Hey guys, what's going on? So today we're going to be talking about a huge review of E&M within the context of general relativity and conformal transformations. These are the two big topics that we've been talking about for the past few videos. And so without further ado, make sure to hit that like and subscribe button. Make sure to go into my Patreon page if you want to support the channel and become a member and get early access to videos and also get exclusive content. And also become a member on YouTube if you want to do that as well. So let's get started. So today we're going to be talking about everything we've been talking about so far. So I'm not going to go through like big derivations and all of that kind of stuff because we did that in detail in earlier videos. This is just going to be, again, a review. And we're going to start off by reviewing the EM portion. So the electromagnetic portion of what we've gone over. So we're going to start off right here actually. This is a basic picture that you probably seen before, which is you have this manifold. It's an n-dimensional manifold, and at each point on the manifold, you can construct a tangent space at the point P. So this is a tangent space at point P, and of M. M is the manifold, right? So M is the name of the manifold. P is the point on the manifold, and this whole thing is a tangent space. We have this notion of a metric, which makes it a metric space, which is this object. Okay, and then from that we can create tensors that mimic the effects of this metric, and that's the metric tensor. Okay, and we can construct these spaces here, a tangent space at the point P. The dimensions here is the dimensions of the manifold. Okay. So we're just talking about E and M for right now. Actually, I'll keep all that. We're just talking about E and M for right now, but later. So we're not really touching on all the tensors and stuff that we've gone over. Sort of the elementary Ricci tensor, Riemann tensor, and so forth. We're not going to be going over that. We're going over some of the more advanced stuff that we've gone over. Okay, so keeping on focus with E and M, we were then able to say, okay, well, we can construct this F mu nu, right? This F mu nu is this the electromagnetic field tensor, and we can construct F bar mu nu. This is the dual, and the effect of dualing this object is on a matrix. Explicitly looks like this. And when we act with each one of these matrices on some velocity vector, we get these objects here, right? So these objects are this is the electric component, and these are the magnetic components. Okay, and then going even further, we could take derivatives. All right, we can take derivatives of these, and from these derivatives we can get the inhomogeneous and homogeneous Maxwell equations. Right, so really encompassing, so these F mu nu's really encompass everything. But sort of at the heart of these F mu nu's again is the potential. Right, so the potential looks like I actually don't have the potential listed here. It's the A vector, right? So A mu. I thought I had it somewhere in here. Oh, here. This A. These are the real driving forces. This is the potential that make up these objects. Okay. So these guys drive the F mu nu's, right? So these are the driving. So these guys here are the driving forces to everything, right? And they're also all hidden in these equations as well. So again, the inhomogeneous equations and then the homogeneous equations. And then we can take these guys, we could take the F mu nu, and we could take F bar mu nu and construct something called a bivector, right? So a bivector, a self-dual bivector, right? So it's the self-dual bivector. I'll write that down. Self-dual UAL self-dual bivector. The reason it's called self-dual is because it contains its dual within itself. Okay, and now that we have, we can understand these guys in terms of these matrices, and ultimately what we get is when we fill these in, we get these guys right here. So our mu's, these are our velocity vectors that we had over here, right? And so we went in quite detail how we got from these guys to these guys in earlier videos, and you can go back and look at that. However, the point is that we can have a real part, we have an imaginary part. These together, when we contract the self-dual contraction, I'll call this self-dual contraction. Well, that to us looks like a number. It's right. We have a real part and an imaginary part. Okay. So we've gone over that. Let's take this root now. Right. So if we take this root, again, so I'll erase this. We're also able to show that this here, so this is something you actually might see in like a standard QFT course or a gauge theory course or something like that. So this shouldn't be new. Then we were also able to show this, right? So this was the electromagnetic, this is the stress energy momentum tensor, but in terms of the electromagnetic field. Okay, and the idea here is that the electromagnetic field can also be a source of curvature in spacetime, right? Because in Einstein's field equations, recall, we had G, right? So G mu nu is equal to, or is proportional, we'll say it's proportional to T mu nu. And we say T mu nu is equal to all of this. Right, so we're saying that this is proportional to all of this, and this is all phrased in terms of the electromagnetic field. Right, so the idea is that this is geometry, this is geometry, this is mass, this is electromagnetism. All right. Okay, and so we also have the electromagnetic stress tensor T mu nu, phrased as a matrix. I'm not going to go over this in detail because we already have done this, but the idea here is we can actually understand the components of T mu nu. Okay, so we have, so this is our this component of our T mu nu. This is the temporal component, and then we have all these mixed components, right? Mixed components. These are all mixed components, and the yellow here are the non-mixed components, and right, so we have our legend here: energy density, momentum density, energy flux, shear stress, and pressure, just like in our typical stress, energy, and momentum tensor. All right, going up here, we are now so we now have we want to look at an action principle. The action principle is going to be, we proposed that we had the Einstein-Hilbert action. The Einstein-Hilbert action looked like this, and this gives rise to Einstein's field equation. So Einstein's equations of motion, right? And we also had, and so now we're hacking on this part here, this M part, or the Maxwell part. So the Maxwell part is this guy right here, and we were able to show that with this we can get this. Okay, we were also able to see electromagnetic tensor null conditions, right? So if we have really what this is we want to find, we had a vector basis. Right? So our vector basis that we defined was had a temporal component and an x component. And when we did that, we found that our EM tensors, right? So F mu nu and F bar mu nu, in this case I just have labeled alpha beta, look like this. Okay, they look like this. So we have our y components and our bz components. We have bz, and ey components. If we set the ey components equal to the bz components, then our stress energy tensor becomes this. Okay? And so this sort of flows into the idea here where we now have a matrix, an electromagnetic field tensor matrix, in which if we were to travel in, say, this direction, our potential electromagnetic 4 vector becomes this. So we have two vectors then. We have an eigenvector for this condition. Okay, we can construct eigenvectors for other conditions, right? But this condition happens to be the null condition. We're going to call the null condition. And we also have the potential electromagnetic 4 vector. Okay, and this here, or this object here, can act on this object here. Okay, and you should be able to get something that looks like this, right? Because you multiply this by this, well, you get that EY component. Do the same, and you get the BZ component. Right here, then you would do, yeah, and so yeah, I'm not going to get too much into this. I could go down a rabbit hole. We've already talked about this before. And yeah, so those are that's what we briefly touched on null conditions in this. And we will probably go over this a little bit more just to solidify our understanding later when we start talking about charged black holes. Right? All right. Again, all of this I'm doing because we are aiming towards the point of trying to understand charge within the context of curvature. Okay, specifically within the context of electromagnetically charged black holes. All right, so the complex electromagnetic vector becomes this, and so we have an E component and a B component, right? So the E component is the electric component, B component is magnetic component. And this is going to be our vector. Now this is weird, right? Because this is a vector and this is a vector. So this is, in some sense, a bivector, right? Because it's a vector of vectors. So this is really a bivector. And this is an arbitrarily rotated, you could sort of think of this as an arbitrarily rotated electromagnetic field tensor, right? Because our electromagnetic field tensor is right here, right? So right here, and our electromagnetic field tensor contains the E vector, the electromagnetic vector, and it also contains the magnetic part, right? So it contains the electric part and the magnetic part. And so if we were to say that the electric part is the real part and the magnetic part is the imaginary part, well then we can use this to define an this E tensor. We can define the right and the left dual of this E tensor, which we've done before, and in that way we were able to define these two guys, right? So if this is a little bit confusing to you, I would urge you in going back and looking at the video that covered this, and so you can understand this a little bit more. Again, this is just a review. I'm not going to go into too much detail here. And this E tensor, right, this E tensor here is, we can identify as the Ricci curvature tensor. So this is going to give us some interesting insights, right, because identifying this E tensor here with this E tensor here is going to show us that we can go through a series of steps by understanding how the right dual of this E tensor can actually give us an interesting formula for the Ricci curvature tensor, right? And ultimately we get to a point where we could say that the Ricci curvature tensor is actually a special case of this E tensor. And this E tensor, in terms of the electromagnetic bivector, looks like this, okay? Where we're really summing over rho. We're summing over rho in both cases here. And then we came to this notion of a complexion. Right? A complexion was, well, you take this F vector. Right? This is a little bit blurry. You take this F vector. This F vector is again is a vector of vectors, but you still have this concept of rotation going on because it is a vector. And the complexion is the angle by which this has rotated. And this is an invariant object under Lorentz transformations, as we've mentioned before. And this object since it's an angle, it's a number, it's a scalar, we can actually produce a scalar field at every point on the manifold. Okay? And this is how we came to an equation for this actually. So the equation was a full contraction of the Riemann or the Ricci curvature tensor with itself. And then we have all the summing over properties and stuff like this with the covariant derivative and raising of the indices here. The point is that this is an invariant object under these types of Lorentz transformations. I shouldn't say these Lorentz transformations. We haven't really gone over Lorentz transformations that much. What I should say is that this is an invariant object, and we'll just keep it at that for right now. All right, so we talked about this a little bit, right? So Ricci curvature, scalar curvature. This is a more general case of scalar curvature, and then we have our Weyl curvature. In some sense, we really want to come back to this picture when we start talking about conformality, because the idea here is that these are really just general cases of what we know as Ricci, the Ricci tensor and the Ricci scalar. Right, so these are, what's nice about these things is that they all have the same symmetries as the Riemann curvature tensor. Okay, and when we came to that realization, we found that we can do some very, very interesting things with these objects regarding making them complex. And then we talked about the range conditions again. So range conditions, we assume that the space-time is source-free, and in this source-free case, we have this condition, and because the electromagnetic components must be greater than or equal to 0, we get these conditions. Right. So this is really just saying that you can't have negative, right? You can't have negative electromagnetic components. So, and then we have lastly, we contract over mu and nu, and we get these objects here. Okay, so these are sort of analogous. The mass term contracted is analogous to the curvature contracted with itself as well. So mass contracted with itself is analogous to curvature contracted with itself, and these are the range conditions. All right, let's move on to conformal transformations. So what we talked about was G mu nu transforming by some scale factor omega, and through this equation we were able to show this right here, and through this we were able to show that the conformal transformation looks a little something like this, right? So this is a solution to this differential equation where x mu nu is location on the manifold, and L is a L is a constant, right? Okay. We also talked, so let's talk about this really quick. We can calculate the Riemann curvature tensor and the Ricci curvature tensor and scalar. And we can see that the relationship between all of these forms is through a B vector, right? So hidden within all of these guys is going to be this B vector, right? This B vector shows up in this guy, B vector shows up here and here, B vector, or not vector, B tensor, right? This B tensor shows up here for the Ricci scalar as well. And this B tensor generally looks like this. It's in terms of the transformation, right? In terms of the transformation, and then the trace of this B tensor looks like this. And you can see that when the dimension, right? So M is the dimension, the dimensionality of the manifold. When the dimensionality of the manifold is 4, something quite interesting happens. The trace of this guy goes to 0, right? If the dimension, so the trace of this guy goes to 0, that means this goes to 0. That means that the conformally transformed Ricci scalar is just this times this, and that is analogous to this. The only exception is that this isn't positive, this is negative in this case, right? So you can see that right here. I won't belabor this point too much. Again, so if M equals 4 here, well, you still have this here, so you still get something non-zero in the case of the conformally transformed Ricci tensor. All right, so that's something to think about, right? When M equals 4, interesting things happen, right? The Ricci scalar doesn't change. It doesn't say it doesn't change. It changes by this factor, right? It changes inversely to how the metric changes, and that's interesting. Something to think about. And then we talked about the Russell-Length identity. This identity, we had this right-left duality, and we had these projections. What's more interesting here, I think, is that these things are traces of these things. And we talked about that, right? So these guys here are traces of this more general W matrix. Right, so and so we can use this equation to understand the geometric meaning of the left-right dual tensor, which is this, right? So this is the Einstein field equations, or the Einstein tensor, right? And the right-left dual operator on the Ricci tensor is equal to the Einstein tensor as well, right? So again, so you can calculate the right-left dual of the Ricci tensor just by understanding what the Einstein tensor looks like. Okay, so this is actually quite interesting, right? Because if you recall, so G mu nu is equal to, it's proportional to T mu nu, and so it's equal to a proportionality constant times T mu nu. This is saying that this is the same thing as saying R mu nu is proportional to T mu nu. Right, so right off the bat, you could see here that there is a very interesting relationship between, there's an operation you can do on the Ricci tensor that gives you the stress energy momentum tensor. And in our case now, the stress energy momentum electromagnetic tensor, which is this guy. So we could stipulate the structure of complex tensors, where we say the right dual of these tensors is the complex part of these more general tensors. And what this gives us is Petrov classifications of these tensors, right? So if the right dual is the complex component of a complex tensor, then the left dual of the complex tensor is the complex, or if the left dual of the complex tensor is I times the complex tensor, right? And so we have for each one of these, right? So in the vial case, in the Ricci case, and in the scalar case. And we'll come back to this later. This is somewhat advanced stuff, so we'll come back to this later. It's not necessary right now. So the part of the Riemann curvature tensor that remains invariant under the conformal transformations and is also a traceless part of the Riemann curvature tensor we saw is the vial tensor. So this is just quickly going over the vial tensor. We had this volume-related curvature or volume-induced curvature, and then area-induced curvature as well. Right, and you can see, this is interesting, right? So if m equals 4, as we mentioned before, well, this is going to be 2 times 3. Well, this is going to be 6, right? So the dimensionality of our manifold when m equals 4 is actually, this thing is actually not, it's not 0. However, if m equals 2, or if m equals 1, right? If m equals 1 or 2, then all of a sudden, we don't have a source of curvature anymore, right? Because we identify source freeness with the Ricci scalar, okay? And so that's quite interesting, right? This is so the deviation in the area no longer plays a role in defining our curvature if we constrict ourselves to only a dimensionality of 2 or 1. But these guys are still free to move around, right? If m equals 2, however, then this thing goes to 0. So, what's going on here? We're seeing that if m equals 2, something quite interesting happens. If m equals 2, this goes away, and this goes away. So, if m equals 2, then r kappa lambda mu nu equals c kappa lambda mu nu. So m equals 2 is a very, very interesting thing, and I'll end on this. Right, so last time I talked about Terence Howard, and I do want to get into talking about his kind of insights on a few things. Again, a lot of what I think he said was wrong, but there's something quite interesting that I don't think, if he were to study this kind of topic, he would come to some marvelous insight here. The marvelous insight is, when he was talking about how 2 was special on that 4-hour-long thing with Joe Rogan, this is one of the reasons 2 is quite special, right? If the dimensionality of our manifold is 2, right, then our Riemann curvature tensor equals the Ricci curvature tensor. And that's quite interesting, right? Because, again, the vials, I don't know what I said when I boxed this, but what I meant was the vial tensor, right? So this is Riemann, and this is vial. And this case right here, m equals 2, that gives us this, right? If m equals 1, if m equals 1, that's quite interesting also, right? Because what happens here is, if m equals 1, this thing here becomes negative, right? Because 1 minus 2. So we get c plus all of this, right? So this no longer becomes a positive sign. So we get c plus all of this, however, plus nothing else, right? Plus 0, right? Because if m equals 1, this is 0. And then this becomes undefined. So things actually don't work. If m equals 1, right? Because this thing's undefined, and you can't add something undefined with something defined, right? And so really things only start getting interesting when m equals 3, and so forth. So that's something to think about, and that's something we're going to explore a little bit more later. But what I want to do now is just stop here, because in the next video on GR, we are going to start going into the Schwarzschild metric. and then the Kerr metric, and then we'll start exploring metrics and solutions to Einstein's field equation. So with that being said, make sure to hit that like and subscribe button. Make sure to go onto my Patreon page if you want to support the channel. And with that being said, I will see you guys in the next video. Bye.